Hi everyone and welcome to Activity 15. Today we are going to talk about periodic functions. Periodic functions or periodic situations are functions that repeat themselves after a certain period of time, right? It takes one period to create one full cycle and then the graph or the situation will repeat itself. So some common examples you can see below, sound waves, seasonal temperature changes, ocean times, pendulums swinging back and forth, rotational motion, things going in circles, electric currents, population cycles, heartbeats, daylight hours, vibrations. These are all some common examples of our periodic functions. Now, some key terminology then with these periodic functions. A period itself is the amount of time it takes to make one complete cycle in our situation or on our graph. The amplitude then is half the distance from the max to the min in our situation. Our midline then is the average of the max and the min. Okay. And while we see a lot of graphs with like a wave situation, that's not all of them, but the main key feature is that period and how long it's taking our graph to repeat. So in this first example of kind of a real life situation, we have the real wheel of a riverboat that has a spoke that starts 5 feet below sea level. So if we think about this wheel, it's starting 5 feet below. At its peak, it's rising 5 feet out of the water. And at its cruising speed, it's taking 8 seconds to make that revolution. So we're down 5 feet below, 5 feet above, and then again, that time it's taking to make that cycle is 8 seconds. And we want to sketch a graph of this situation. So what we see here, 1, 2, 3, 4, 5, 6, 7, 8, is our period. In this case, it would take 8 seconds to see that whole graph. We are starting 5 units below, and our max outside of the graph is going to be 5 units above. So in this case, we start again 5 units below, and it'll take 8 seconds to get back down to that point. Halfway through is when we would hit our peak, so 4 seconds in, and again we see this graph as we sketch through, something like that. And again, as the wheel on the boat goes in its circle, we would see, for instance, 12 seconds in, kind of the next cycle of our graph be up halfway through here, and then repeating that cycle through. Another example is if they are actually giving us a graph of a situation. In this case, they want us to state the following. So the time it's taking our graph to go up, down, all the way back to the beginning, in this case, max to max, that's our period. That's 3 seconds. The amplitude is half the distance between the max and the min. So this total distance is 4 units. If we cut that in half, 2 this time would be our amplitude. Another way of thinking about that is that our amplitude is the distance from the midline to the max. That's another way of thinking of that amplitude. Speaking of midline, this time our midline actually is the x-axis through y equals 0 would be the midline that we could draw in halfway between our max and our min. Now, what type of transformations are going to affect each of these key features? Well, in the case of a period, a horizontal stretch or shrink will affect that period, right? It's going to cause our graph to either repeat quicker or slower. So a stretch would stretch it out versus a shrink that should make it repeat more and more often. The next thing that would affect our parameters on our graph would be a vertical stretch or shrink. And what this is going to affect is the amplitude. Because what it's doing is it's going to take our graph and go from being, this size, for instance, to either stretching it out to be bigger or shrinking it down to be smaller, affecting that amplitude based on our stretch. Finally, a vertical shift is going to affect our midline because you're either going to be moving that graph up or down, which essentially again will affect this midline to either shift up or down, depending on where you're shifting it vertically. All right, example 4, speaking of parameters, says that one year we have a temperature recorded in a city that is 90 degrees is the high, and the lowest was -10. The next year, we recorded 100 is the high and -20. What features of our graph would this change? Well, in this case, if we have a high temperature of 90, low temperature of -10, in between these two, that's a distance of 100 degrees. So in this case, the amplitude would be 50. Midline would be halfway between there. In this case, if we took the average of these two, 90 plus -10 divided by 2 would be through y equals 40. So this would be 50, would be our amplitude. So that's kind of some things of the first graph. Time it's taking to repeat is 1 year, right? Well, if we think about the high and the low over here, we said the 100 is the high, -20 is the low. Distance between these two is 120 units, so our amplitude is 60 this time. The midline, though, is still 100 plus -20, which is 80, divided by 2, so this is still 40. Time that we are analyzing is still over the course of 1 year. So the feature that changed this time is our amplitude. And the reason being, we stretched our graph, our max and our min out, so now we're stretching out, increasing that amplitude for that second year of data. On our next example, we have a child on a swing at a park, swinging back and forth, so think about like we have a child here going up and down, and they have a friend who comes and moves them faster, so that as they're going up and down, it's going faster and faster and faster. What feature of the graph is this going to change? Well, this is going to change our period because we are making quicker. If we're moving faster, we're making more revolutions, so that's going to change the period, the time it takes to repeat. Maybe the child swung back and forth every 2 seconds before, and now they're swinging back and forth every 1 second. That changes your period. Thanks everyone for watching. We will work more with these in class.